Welcome to the video on Chapter 6, dealing with methods. And let's get into a program that demonstrates the importance of methods. This is basically code that's in the textbook. Greatest common divisor method. Okay, fine. And so this is the class that we're going to take a look at. I embellished the code here and there to show you my explanations. But first things first, we've been using methods since day one. I mean, at the very start, we had a main method, and that main method executes the very first time you run the program. When you run the program, that main method executes, and all the logic inside that main method is executed from top down. Now, this main method is nice, but you need to break your logic up into smaller methods. Now, for instance, in this problem, there's a method called GCD. Well, first off, what's GCD? The greatest common divisor is the biggest number that divides into two other numbers. So if I take this GCD, and the nice thing about methods is that you don't need comments. I mean, by looking at this method, you see the GCD, okay, greatest common divisor of these two numbers. So you think of a method as like a subprogram that takes input, in this case 24 and 36, does some magic, and returns a value which hopefully will be the number 12. So that number 12 gets returned and stored into that variable. Now, that same subprogram, that same method, takes two other numbers, 48 and 72, and that algorithm gets executed on those two numbers, and hopefully the number 24 comes back, because that's the biggest number that divides into 48 and 72 evenly. And what do you think the biggest number that divides into 15 and 17 is? Well, if 17 is a prime number, the biggest number that divides into those two numbers is the number 1. And then I print those numbers out to see if they in fact work. But the nice thing about methods is you have only one copy of the algorithm. Okay, and that algorithm is enveloped inside a method called GCD. And you call that method 3 times. So you basically have one copy of the code, and that copy of the code takes different inputs. See, methods tend to make your program smaller because you're not duplicating this algorithm 3 times, which means that you have to duplicate the code necessary to get the GCD 3 times. Basically, you just have one copy of the code. That code takes in inputs. These are the actual parameters that get sent to the algorithm. And then as far as I'm concerned, the main method doesn't really care how the GCD gets produced, as hopefully the number that comes back is correct. The main method just cares that the algorithm is correct and comes back with a number that's proper. We go into GCD1, we store that. So basically you get smaller code, and you get to reuse this method in other programs. You just you copy the code and you plug it in to other methods without worrying about having to debug that algorithm, because you know it basically works. So let's see if this works. Let's run this. I didn't show you the algorithm yet, but let's just have a little. Yeah, it seems like it works right there. See, 12, 24, and 1. The output really should be formatted better to tell me what those numbers are, but we know that basically we're just testing the system out. And then we go into the second part of the main method, which is this is the problem with these with this first set of calculations, that those are fixed numbers. Fixed numbers just demonstrate the validity of the code, but it doesn't produce a program that's useful. So what I want to do is I'm going to get rid of all that stuff right there, get rid of that, because really I want a more flexible program, and a more flexible program will require me to read those numbers in from the keyboard. And that's what I'm doing. I create my scanner, I prompt for the first number and 1, second number and 2, And then I go ahead and probably a better way to do this is to say integer, let's call GCD, some method that I haven't described yet. And this time I'm going to call GCD with the numbers n1, comma n2, those values. And what comes back is an integer, which is my answer. And my answer is going to get the calculation of GCD, okay, whatever I type in. And I have a nice little prompt in my output. The greatest common divisor for n1 and n2 is, and I'm going to put my answer in there. And that's the main program. Now, there's a whole bunch of ways to do this GCD. Here's the way they describe in the book. Okay, now when I look at this method here, I don't worry about the main method. The main method did its thing. It called GCD. It passed that information into GCD. Whatever numbers got typed in gets passed into those methods. And by the way, this N1 and this N1 are different. Okay? Notice even Eclipse is telling you that. Let me just expand this a little bit. Eclipse is even telling you that because if I highlight N1, N1 basically, when all the highlights show the scope of where N1 is defined. This N1 is not the same thing as this N1. N1 here are local variables to the methods. N1, N2 that's defined inside the main method are local to the main method, only seen there. This N1, N2 are local to this method here. The only relationship is that these parameters, called the actual parameters, whatever value got typed, if I typed in 33, 33 gets sent to another variable passed by value. So this N1 gets 33, and if I typed in 24, that 24 gets sent. This 24 is in this value as well as sent here. So think of these as just local. Think of these parameters, they call those the formal parameters, as being conveniently initialized local variables to the GCD method. And this is typically what happens here. You know, and the way you describe, you create a method is you gotta give it a name. This is what I do. So I call it GCD. Then the set of parameters, the pieces of information that this algorithm needs to work on. And then the return value has to be specified, the data type of the return value. Well, if I pass it two integers, the GCD has to be an integer. And for now, other than the main method, define those methods as being private and static. This is just to get it to compile. The idea behind public is that the method gets to be called by external sources. Okay, so this main method here can be called by the JDK. So you're allowing the JDK to run this code. You're not allowing the JDK to even access GCD because you defined it as private. It's called the need to know principle. The world doesn't need to know how you do things. Only you do. The main method can call this GCD because it's inside the same class. So anything inside the same class is always executed. This is the point of view of the world, the external world, the world being outside this class. Okay, so you're allowing the world to see the main method, and you're not allowing the world to see the GCD. It's called the need to know principle. And just define all your methods as private unless you know exactly what you're trying to do. And then all methods are static right now, and I'll leave it at that. Don't remove the word static. It won't compile and won't work. In due time, I'll describe what the word static does for you. Okay, so private, static, return value, integer, GCD. And so now before we start writing the code, here's the code right here. We have the braces, and inside those braces we have to have some code. The idea, the textbook's way of doing this is they say, well, start with a factor equal to 1. Okay, start with the factor of equal to 1, and as long as that factor is less than or equal to both numbers, try dividing that factor into n1, n2. And if you can divide those numbers evenly, okay, into both numbers, then that's a possible candidate. Okay, well, certainly 1 can divide into n1, and we notice we have the mod operator. It divides into n1 evenly because we know it returns 0. Okay, so that factor of 1 will certainly get put into GCD right there. Okay, now try 2. Okay, so if I typed in 24 and 36, well, 2 will divide into 24 and 36 evenly, okay, because 2 is less than 24 and 36, and it would divide evenly. So another candidate is whatever GCD we had was 1, now it becomes 2. So we start incrementing factor until we hit the smallest number, okay? Because when you get past the smallest number, obviously, when you get back, if the numbers were 24 and 36, okay, if you try to go to 25 obviously can't divide into 24 evenly, so you stop the process. So this is what this is doing here, and what we're going to do is just report back on the biggest number that we encountered as dividing evenly. Now, this is not the best algorithm, but it is an algorithm, and it does work as we see. So if we go ahead and rerun this, okay, we'll type in let's see, 36 and 24. Hey, there it is. The number is 12. But that's great. But you sleep on it, you come up with different algorithms that you should probably look at. And so I thought about it, and I said, well, why don't we do this? Instead of working our algorithm going from 1 to a big number, why don't we go to the big numbers and work downwards? Okay? And so if we try, say, 36 and 24, why don't we start with the 24? Okay? Well, 24 doesn't divide into 36 and 24 evenly, so both numbers. Then you try 23, 22, 21. As soon as you find a number working yourself down, then that's the greatest common factor. Most of the time, that will be the fastest algorithm. So what I propose is another algorithm, another method here. Okay, and so I'm going to push this other code down so you don't see it. I call this GCD2 because you can't have two methods called the same GCD with the same parameters. So for now, what I'm going to do is, I'm going to comment this out. I'm not going to delete that code. Source toggle comment right there. I'm going to comment that out because I basically want to save that code. It's still good code, and I'm going to experiment with other code. So I'm going to call this GCD. And what I do is I try to find the minimum value of those two numbers that I pass it. So 36 and 24, the minimum should come back to be 24. And notice what I'm doing is I'm using a method that's defined in the main class. There's a minimum method that's defined in the main class. I pass it 24 and 36. And magically what comes out is 24. Now in this case, I'm going to use a for loop just to show you for loops. We try the factors from 24. We're going to decrement the number as opposed to increment it up here. And as long as the factor is bigger than 1, try the number. The same if statement. If the factor divides evenly into n1 and divides evenly into n2, just return that number. At that point, just return that number. That's a nice way of doing it. The return stops the code that's inside this method. It stops and returns the value immediately back to the main program that called you. Now, if you tried every factor, if you tried every factor that's bigger than 1, so you tried everything. Say you had a number 101 and 33. Now 101 is a prime number. You try 33, 32, 31. Eventually you get down to 1, and you didn't find a number that divides evenly. When the execution comes here, line 40, I know for a fact I tried every number, I exhausted every possibility, but the GCD at that point has got to be the number 1. Okay? It's got to be the number 1 because that's the biggest number that divides into those two. Well, let's see if that works. Let's see if this coding works here. So I'm going to push this up, run it. Okay. Let's see, 101 and 33. That tests out the case where we have a prime number. And how about 24 and 36? And that's 12. Yes, great. Now even this guy, see, the nice thing about this is I changed the logic of the GCD. The main program didn't need to be changed. The main program was relying on you to develop a method that works properly, and it didn't really care how you generated that answer. It just reports on the answer. That's the nice way of looking at it. Now, I'm going to comment this out too, because I'm going to show you 2 other ways to do this, which are pretty neat. Let me comment this out, toggle that. And I have a 3rd version, and this 3rd version is called Euler's method. And I'm going to call this GCD, okay, right there. Notice the same signature, same exact signature. So from the point of view of the main program, it doesn't care, okay? It just says, I'm going to pass you 2 numbers, and you return back a number. And this is Euler's method here, which says, okay, let's try 36 and 24. And it turns out that if you divide 24 into 36, what do you get for a remainder? 12. Okay? Keep doing that with every 2. So work with these 2 numbers to generate a remainder. We're going to generate a series. Okay. Now work with these 2 numbers. 12 goes into 24, generates a remainder of 0. As soon as you generate a remainder of 0, stop. And the number just before the 0 is the method. It is the GCD. It always works out nice. And so basically, you're generating a series. You divide the smaller number into the bigger number, but you're worried about the remainder. Certainly 24 goes into 36 1 time, but that's not important to me. I want the remainder. So then what happens is I internally generate a 12 as the remainder. The 36 did its job. Switched the positions of 24 and 12. So in other words, let me just show you this in terms of the numbers, the things that below here. This would be considered N1, and this would be considered N2 in my algorithm down here. All right, so for the first iteration, this is your remainder. And let me put a little space in between here so it doesn't look so smushed together. Okay, right there. All right, so first iteration, 24 goes into 36, I generate a remainder. Okay, now what happens is I do another iteration, and this 24 now becomes N1. This 24 now becomes N1. The remainder now becomes N2. I perform the division and keep the remainder. I get the 0, and I stop the process. Okay, and then I report back on the previous number N2 that's located N2. So it's very fast. A couple of iterations, we got this answer done. So I'm going to do this logic while true. Certainly a do loop, because you have to do this logic at least once, and a do loop is fine for that. Do your logic at least once, calculate the remainder. If your remainder is equal to 0, break out of the loop, you're done. And once you break out of the loop, return whatever value is in N2. Notice right here. Now, if it's not 0, okay, whatever value is N2 gets assigned to N1, right here. What's in the remainder goes into N2, and you start the process over again. Eventually, you're going to break out to return N2. Let's see if that works. My favorite numbers, 36 and 24. Okay. It even works if you change the numbers and put them in different orders, 24 and 36. It works out nice. Okay. So that's good. And then I want to show you the last way of doing this. This is the more straightforward way of doing this. source toggle this code. I don't want to throw away this code because I love this code and it works. See, what happens is if you experiment with new code, you want to go back to you can always go back to previous code because you had it worked, and you just want to improve the code. But if you can't improve the code, then you can always fall back on something that does work. So this is the very last method here, and get rid of that. Basically, this is the same version as this one, and I'm going to show you a real cool way of doing this. Now, in my while statement, I have a variable remainder. Okay, that's good. I need a variable remainder. And so inside my while loop, what I'm going to do is I'm going to calculate n1 mod n2 and assign it into remainder. This might get a little complicated, but this is the way you did this back in C, C++, and now Java. You do your calculation in the while loop. So 36 mod 24 gets assigned 12 as your remainder. Now every operator, even the assignment, returns a value, 12. So what I got highlighted here in those parentheses, now I have to have the parentheses because I want to force the compiler to do that assignment first. 12 does not equal 0. Okay, the remainder, see, the value of an assignment is what got assigned. What got assigned to remainder is 12. It's not equal to 0. So now for the next iteration, what I'm going to do is I'm going to do the same thing here, switch the positions of n2 and remainder. n1 becomes n2, n2 becomes the remainder, and do the process again. Okay, and then what we're going to have here is 24 mod 12 gets assigned 0 into the remainder. 0 gets compared to 0. 0 not equal to 0 is false. It is equal to 0. We exit, and 2 gets returned. Same. It's basically a shortened version of this. And I think that if you understand this, you understand C, C++, etc. So let's try this to prove to you that this works. And I'm going to have 24, 36, and it works. And it works for everything here. Let's try 101, 33, 1. Good. So let's stop the video here and tell you what's wrong with this program. What's wrong with this program right now is that I'm getting carpal tunnel, always having to come over here and push this button, and then I have to enter my buttons here, my numbers 10 and 24. Then I have to do it again. I have to come over here and restart the program. I don't want to restart the program until I tell it to stop explicitly. So I'm going to show you a template that you need to use in your code. There's also another, so that basically loops and loops and loops until you tell it to stop, and then it's a better format to submit your code. Also, don't submit this because there's no name, there's no global information. So I'm going to show you inside the template. If you use the template, it forces you to type, to put your name and what this program does, etc. So I'll stop the video here, and the next video I'm going to introduce you to the template, which you need to use in your program. All right, we'll see you in the next video. Bye.